Hello there, Mr. Sutton bringing you the AB Calculus 6-4 Extra Practice 2 solutions on differential equation practice. On this problem, we have the temperature inside a fridge given by the function W, and that satisfies this differential equation here. Let's see, W is in Celsius, T is in hours, and at time 0, the temperature inside the fridge is 3 degrees Celsius. First part, they want an equation for the line tangent to the graph of W at the point where T is 0. And then use it to approximate the temperature inside at time 0.4. So I'm going to use my tangent line setup here. In this case, I'm going to say L of t equals W of 0, because 0 is my launching off t value, plus W prime of 0 times t minus 0. This is just kind of f of a plus f prime of a times x minus a reasoning here. And then W prime of 0, that's what I get when I plug in 0 for t in this differential equation here. But you'll notice I also need to plug in something for W. They told us at time 0, the temperature W is 3. So I'm going to be doing 3 times cosine of 0 over 2 times 3, plugging in 0 and 3 to my differential equation. Cosine of 0 is 1, so that's 3 over 6 here, so that's just 1/2. So then we've got 3, which was W of 0, plus 1/2 T. And now I want to use that to approximate the temperature at 0.4. So I can just plug 0.4 into this function I just wrote here. Now, since I'm plugging it into the L function, I can write equals. If I wanted to write this as a W of 0.4, I would need to write approximately equals, because this is an approximation. 3 plus half of 0.4, that's 3 plus 0.2, comes out to 3.2 degrees Celsius. For this problem, they want the particular solution to our differential equation, given W of 0 equals 3 as our initial condition. Since I have an output variable, W, in the differential equation, I need to separate my variables. I'll start by multiplying W to be with the dW on the left side, and I'll move a 2 over there as well, because why not? Normally, I wouldn't do that, but my reasoning is when I do take this antiderivative, I'm going to be dividing by 2. So if I've already got a 2 over there, I don't have to mess around with a 1/2. Anyway, over on the right side, I'm just going to have 3 cosine of t times dt. Now for my antiderivatives, this is going to be W squared on the left side. On the right side, this becomes 3 sine of t plus c. Now I have to plug in my initial conditions, 0, 3. So I've got 3 squared on the left, and 3 sine of 0 plus c on the right. Well, sine of 0 is just 0, so we really just have c on the right side. So c then equals 9. Now I'm going to go ahead and plug 9 back in for c in my general solution. And to isolate y, or w rather, it's w, not y on this problem, I just have to square root both sides of the equation, but I have to pick either the positive or the negative root. I can't have both. So looking at my initial condition, my first w value, my initial w is 3. That's a positive number, so w has to always be positive then for this problem. So that means that I'm going to be doing w equals the positive square root of 3 sine of t plus 9. For this problem, they're saying that the temperature in the kitchen is a constant 20 degrees Celsius. Cost of operating the fridge goes up at a rate of 0.001 per hour for each degree the temperature in the kitchen exceeds the temperature in the fridge. So in other words, the colder you're trying to keep your fridge relative to the kitchen, the more it's going to cost you. So write but do not evaluate an expression with an integral to find the cost of operating our fridge for 24 hours. Well, we need an integral, and it would make sense for it to go from 0 to 24, because that's the cost we want to find for this fridge, the time we want to find that cost over. Next, what are we adding up over that interval? So we have to have a function for figuring out the cost of the fridge at any given point in time. So we're told that it's going to be 0.001 per hour, so let's put that in there. And what do we have to multiply that by? We have to multiply it by the difference between the kitchen temperature and the fridge temperature, which we can write as 20, because it's a constant 20 for the kitchen, minus our fridge temperature of W of t. We have a dt there because these are time units, 0 and 24. And don't forget, this is going to be measured in dollars, so let's stick that on the end just so we don't get dinged for omitting units. On this problem, they're giving us this differential equation up here and some particular solution for it, f of x. They're saying a portion of the slope field for this is given below. We want to sketch the solution curve through the point 0, 1. Well, let's start by plotting the point 0, 1. It's right here. And I just have to draw a curve that goes through that and follows the tangent lines. So let me go to the right first. My curve's going to look something like this, following those tangent lines. And going to the left, we have something that looks roughly like this. There we go. And there it is. For this part of the problem, they want the equation of a line tangent to the solution curve at the point 0, 1, and then use it to approximate f of 0.2. So for tangent line approximations, I'm going to go with L of x equals, we'll say f of 0 plus f prime of 0 times x minus 0. And we're using 0 because that's our launching off point. That's the point that we have some information about. For example, f of 0 is 1, so we could actually plug something in there. We do need to find f prime of 0, though. That's what I get when I plug 0 in for x in my differential equation. When I plug 0 in for x, I have to also plug in 1 for y. So this is going to be 3 minus 1 times cosine of 0. And let's see here. Cosine of 0, there we go. Cosine of 0 is 1. This is just 1 times 2, which is 2. So when the dust settles, we've got 1 plus 2 times x. So x minus 0, or just x. Approximating f of 0.2, that's going to be approximately equal to 1 plus 2 times 0.2. So this is 1 plus 0.4, which is 1.4. For this last part of the problem, they want the particular solution given our initial condition of f of 0 equals 1. Because I have y in the differential equation, I have to move it to the other side to be with the dy. I have to separate variables. So I'm going to write this as 3 minus y to the negative 1 dy equals, and now I'll multiply dx to be over with the cosine of x. Taking my antiderivative, this is really going to be, this is kind of a 1 over 3 minus y situation. So this is going to be negative ln of absolute value of 3 minus y. And I need that negative because I have an inner function tail of negative 1 here. On the right side, this evaluates or integrates to sine of x plus c. Plugging in my initial condition, I've got 1 going in for the y value and 0 going in for x. Sine of 0 is just 0, so I really just have c on the right side. On the left side, this is negative ln of 2. I'm going to plug that in for c in just a moment, but let me figure out what to do with this absolute value expression. Now, my initial condition said I had an initial y value of 1. That means that this expression inside absolute value, 3 minus y, must come out positive, because 3 minus 1 is positive. So that means I can just replace absolute value with parentheses, since I never really needed the absolute value for this initial condition. So I've got negative parentheses, negative ln parentheses 3 minus y equals sine of x minus ln of 2, the c value we just found. All I need to do now is isolate the y. So I'll start by negating both sides. Ln of 3 minus y equals negative sine of x plus ln of 2, or ln of 2 minus sine of x, either of those. Next, we're going to raise e to both sides to get rid of ln. So that's 3 minus y equals e to all that stuff. And as an optional intermediate step, you can take this ln of 2 and make it a 2 coefficient outside the e. Next, I'm going to subtract 3 from both sides. And now I'm going to divide both sides by negative 1. So I can write this as y equals 3 minus 2e to the negative sine of x, and call it a day.